Hello, family. In this lesson, we are finally going to talk about the least squares regression line. So some of you guys noticed in your previous Can You Do and some of the lesson questions from the last lesson that it was referring to a line called the least squares regression line. And today you are going to learn what that least squares regression line is. The good news is that it is the same regression line that we've been talking about for a few lessons now. So when we first learned our regression line, we did it in this lesson, and I wanted you to get used to the idea of a regression line because there was a lot of things around that idea that we needed to talk about. So we talked about the regression line, using our calculator to find it, interpreting slope and y-intercept, and then we went into this idea of residuals and residual plots. So now that we are hopefully feeling pretty comfortable with our regression line, we're going to add in this new element of the least squares regression line. And the only thing that's really new about it is that we are going to learn where the regression line comes from and why it's called the least squares regression line. The explanation is, it's not necessarily complicated, but I think when you are first learning the regression line, adding in this idea of the least squares, how we actually find the regression line, can be a little bit much to add in before we actually feel comfortable with it and have used it a little bit. So now that we're at that place, hopefully we're feeling okay about our regression line. We are now going to talk about, well, where does that regression line come from and how do we determine what the regression line should be? So before we really get into the explanation behind least squares, we're going to take a little bit of notes, and then I'm going to show you a video from the AP board that I think is very helpful in explaining the least squares regression line. Now, I know it can be difficult to maintain attention, especially when you're listening to somebody that you're not familiar with, but stick with it because the video really does give you some great information. So before we get there, though, let's go to our page 419 notes. And let's talk a little bit more about our regression line. So the regression equation, and remember I'm referring to this guy that we've already learned, is sometimes referred to as the prediction line. Why would that be? Why would we sometimes refer to our regression line as the prediction line? Well, that's because we can use it to predict values of the response variable. So that would make sense to me. It makes sense that sometimes we would call the regression line the prediction line. It is also called the line of best fit. It is also called the line of best fit. So why might we call it the line of best fit? Well, it is the line that is closest to all of the points in the scatter plot. So the line of best fit literally means it is the line that fits the scatter plot the best. And we know that it fits the scatter plot the best because it is the line that is closest to all of the points in the scatter plot. So how do we determine that? How do we determine what line is closest to all of the points? How do we determine which is the best regression line? Because you can see here, same scatter plot, two lines. That's what this video that I'm about to play for you is going to explain. How do we find that line of best fit? So that is why that leads us into answering this question. Why is the regression line referred to as the least squared regression line? Because it helps us find the line of best fit, and the name describes how you do that. So I will go to this video now. It's not too long, so hang in there. Try to get as much as you can from it. Sorry, I gotta make it small.
Statisticians,
Just
Mr.
kidding.
Youngsaver here on behalf of the College Board. Today we're entering topic 2.8, least squares regression. In this video, it's going to describe how the least squares regression line, the LSRL, is determined by minimizing the sum of squared residuals. So what exactly are we going to learn today? We're going to learn how to determine the least squares regression line, what the most important properties are of this line, and how we can determine the slope of the least squares regression line using the correlation. So let's look at an example. And this is a context we talked about before. Middle and upper income students have wealth privilege, and often this means that they don't face as many educational barriers as their lower income peers. So many educational systems wonder if there's ways to equalize opportunities for low income students and make good on the promise that education in America is a way to equalize opportunities across boundaries. And a lot of school systems have thought maybe attendance is the solution. For example, if poverty causes low attendance at school and low attendance causes then low test scores, maybe if the attendance were to be changed to become high attendance through different programs that target attendance, then test scores would change as well for different populations. And if you want to see the results of these policies, you can go back to topic 2.5, video 2 on correlation versus causation to see the results of some of these attendance initiatives. But what we focused on was this data set. This was a random sample of 11 students in Texas. And we noticed there was a strong positive correlation between the number of school days they attended, percent of school days they attended, and the number of exam questions they answered correctly on their Algebra 1 exam at the end of the year. So many data sets like this one show a strong, positive, linear relationship between attendance rates and exam performance. But one question I have is, how the heck do we even get this exact linear model in the first place? That's what we're going to explore today. Let's look at a simpler data set. This is a set of X and Y coordinates. And here's one model. I'm going to call it Model A for a linear fit. So that's one model of this data. But what about Model B? Here's another model that could also potentially be a good model of this data. And I'm trying to determine which one is the best one. Model A, Model B. Model A, Model B. It's hard. It's hard to know. So let's try and figure out ways to determine which model is better. Well, we might be able to look at, say, the residuals. That is how our prediction error is in terms of our data points. So maybe using residuals can help us figure out which model is better. So let's look at this point right here. For this point, Model A has a residual of 2, Model B has a residual 1. So it's like Model B is better for predicting that point. But for this point, Model A is a little bit better because the magnitude of the residual is lower in Model A. So the first thought you might have is, well, the line of best fit is a line that minimizes the sum of these residuals. But there might be a problem with that. Let me show you why. Here is a very, very, very simple case, a new case of 3 collinear points. You never see this in real life. It's very difficult to see 3 points exactly in a row in real life. And we know that for this model, the best line is going to be one that connects all of them. Again, you don't see this often in real life, but just knowing as statisticians, people who analyze trends, this is going to be the best model. And here, the sum of the residuals is 0. So that seems like it should be a good fit. This is our best model. But what if I fit this line? It should be pretty clear to you why this line is not a good model of this data. And you can see here we get some residuals, +2 and -2 respectively for those n data points. And when we sum the residuals, because there's a +2 and a -2, they cancel and we get a sum of 0. So is this a good fit? Because it also has the same sum of residuals? Surely not. This cannot be a better fit. So how can we get rid of those negatives that cancel out the positives? Well, we could square these residuals. By squaring, we cancel out that negative. And so when we square the residuals, we get these positive values that we can add together. So when we calculate the residuals squared in both these models for the same data, we see that the sum of squared residuals is much higher for the bad model than for the good model. So we can see that summing the square residuals tends to tell us something about the quality of our models. And that's how we come up with the least squares regression line. It's the linear model that minimizes the sum of squared residuals for a data set. So this is how we got this line in the first place. And of course, most data looks like this. It doesn't look like 3 collinear points. It looks like a bunch of points that may have a trend, but there's some random variation. And so we look at the residuals, and we square the residuals and sum them, and this was the line that when you summed the squared residuals, it minimized that sum. And we use technology, statistical software, calculators to determine that exact equation, but this is kind of what's going on under the hood, behind your calculator, behind the technology to get these linear logs. So there's a couple of properties with the least square regression line I wanted to discuss. First off, this one. Let's talk about what that means. So the mean point, let's look at our data. The data was the X variable, the explanatory variable being percent attendance, the response variable being question correct on that Algebra 1 exam. If you get the mean of all of our X values, we see the mean is 86.4% attendance. And the mean of our Y values shows 41.3 correct answers, the mean performance on this exam. And so if I go back to my least squares regression line and I try and plot this point, so that means I'm going to show 86.4% attendance and then 41.3 answers correct, you'll see that those values collide at the mean point, which is on our least squares regression line. So the least square regression line contains that point.
Okay, so now let's go to our note sheet and summarize what we just learned in this video by filling in the blanks on our note sheet. So I will try to make this video small.
Times the standard deviation.
And then we will go to our note sheet. So how do we know which line is the best model? How do we know which line is closest to all of the points? Well, we look at our residuals. So the least squares regression line is the mathematical way of saying it's the line of best fit. To find the line that is closest to all points in a scatter plot, you need to find the line that minimizes the average distance from the regression line to the points. Recall that the distance between the regression line and each point is called a residual. So really, we need to minimize the average residual. We need to minimize the size of our average residual. This presents a problem because when you add the residuals, the sum often equals 0. Now, I think we should write in the word often because the sum does not always equal 0. When you are trying to find the line of best fit, depending on the line that you have, you may have an average, you may sum your residuals and it not equal 0, especially when you're testing lines, because what your calculator's doing when you find the least squares regression line is it's testing a bunch of lines, calculating the average residual, and then landing on the one that has the smallest. So behind the scenes, your calculator is actually doing a lot of work. So it's not always 0. If you have found the line of best fit, it will be 0. But if you have found a line that does not fit the data well, then your residuals will not sum to 0. They might sum to a different number, but that's still not a good reflection. So if that doesn't make sense, the only thing that you need to remember from this part of the notes is that it doesn't always equal 0. The sum will not always equal 0, but you are going to have an issue with the negative residuals canceling out the positive residuals, and so you will not get an accurate picture of how big your average residual is unless you square them. That's what this sentence is trying to get at. This presents a problem because when you add the residuals, positives will cancel out negatives. The reason why is because the points above the regression line have a positive residual, and the points below the regression line have a negative residual. To work around this problem, we ensure that all residuals are positive by squaring them. And then we have a visual right here of what you were seeing in the video. It's not the same data set. It is the data where we looked at body weight compared to backpack weight for students that were going camping. I included this visual for you so that it could remind you of what you saw in the video. I'm going to put a little note here to summarize what this big paragraph says, is that the summary of this will be the least squares regression line. So the least squares regression line, I'm going to highlight that, minimizes, so I'm writing over here next to this picture, minimizes the sum of the squared residuals. We have to square them because the negatives will cancel out the positives, and that will not give us an accurate picture of our average residual. So it minimizes the distance, the average distance from the points to the regression line. One important property of the least squares regression line that you may see on a multiple choice question is that the point X bar, Y bar is on your regression line. So this means the average of your X values and the average of your Y values is a point on your regression line. Let's be a little bit more specific, and then we'll be done with this part of the lesson and you can try the lesson questions. Let's think about this in terms of the Ford F-150 trucks. What they're saying is whatever our average price is and whatever our average miles driven is, that point will be on this regression line. The average miles driven and the average price will be a point on your regression line. In fact, I believe that I know these values. The average price is 27834 and the average miles driven is 63980. So what that means is about 64,000 and a price of 27,000 is a point on our line. So this would be the point X bar, Y bar. So I guess I should label these. This is X bar, this is Y bar. So that is one property about every single regression, least squares regression line, is that whatever your X and Y values are, the average of each value will be a point on your regression line. So that means this is the average miles driven, this is the average price. Notice for each, it's near the center, which we have seen when we have looked at other data sets. Remember, we want data sets where the mean value and the median value are the same, and that's kind of what you're seeing here. Okay, so now that we have gone through the first part of this lesson, you can now go to the lesson questions. I think there's 3 or 4. One thing to note is that these questions are going to be about things that are not specific to the regression, least squares regression line, meaning you're not going to be asked questions. You'll be asked one question specifically regarding how you find the least squares regression line, but then all of the other questions are questions that you have done before, like talking about residuals, because this is the same regression line that we've been talking about for a few lessons now. So one question specifically having to do with least squared regression line, and then a couple of other questions that are questions I could have asked you in the last lesson or the lesson before, because we've been working with this line for a little while now. Okay, give it a try.